Okay, everyone, thank you for joining today's webinar. Again, this is Kyle Welch with RCR Wireless News, and on today's webinar, we'll be talking about the costly and complex cell site deployment process and the application for remote radiohead and baseband units. To lead our conversation today, we are joined by Emilio Franchi, Senior Product Manager at Rrihs. So with that, I'm going to turn the presentation over to Emilio to really start the discussion on BBU emulation.
All right. Thank you, Kyle. As Kyle mentioned, my name is Emilio Franchi. I'm a Senior Product Manager at Rrihs. And first, I'm going to cover a little bit of just the evolution of the network, get into some basic CPRI terminology, and then we'll dig into BBU emulation. So the network's been evolving over time. So we started off with macro cells, which displayed over here. We've gone to passive DAS. I started adding small cells, lots of microwave links. We are now using remote radio heads with BBUs. In some cases, they're going to a centralized office and known as like a BBU hotel. I don't know if you can see my arrow there. Oops, sorry. And so I guess it's a whole bunch of different technologies coming together, from traditional RF cables to fiber and to small cells, RHs and macros. So traditional macro cells have been around for quite a while. You're just running basically coax up a tower. You usually have tower mounted amplifiers to amplify the signal, so you do have signal loss on those systems going up to the antennas. And everything, including the amplifiers, BBU, anything that created that signal is down at the ground level. Now we've gone into the separation between the remote radio head or remote radio unit down to the BBU down below. So the baseband unit is at ground level. You're running a fiber optic cable up to tower to the remote radio head, and then you just have jumper cables and antennas. Good benefit of this system is the fact that you don't have any RF signal loss through the fiber optic cables. You just have to run power up to the remote radio head. So it does reduce OpEx quite a bit, since you don't have to pay for a larger building, as much air conditioning and so forth for the equipment room. And now we're starting to see what we're calling BBU hotels, different configurations. A CRAN, which is basically a fiber ring that's connected to a centralized office with the BBUs. They're running links to different remote radio heads. And the other thing, which we're calling a star network, which is basically direct fibers from the BBUs at the central office or the hotel directly to the remote radio head. So there's different configurations, but in a sense, it's a centralized place for BBUs. And you also have some virtualization of the network when you're able to do this. And again, lower OpEx costs by lowering energy costs, and also just the cost of the facilities needed. So what's happening in the installation process? So with this basically going to a fiber optic based network. So there's less RF line sweeping. So you're only generally sweeping now jumper cables from the remote radio head to the antennas, and testing the antennas also. And that's usually done at the top of the tower. In some cases, you may do it below just to verify that everything's working before you even climb the tower. You're normally also separating the RF crews from the BBU, so you will install the remote radio head, or somebody will install the remote radio head, the fibers, and so forth, and somebody else will come in later and at the very least commission the BBU. It may install it, if not, but it will not usually get integrated until all the RRH is there, the antennas, the fiber, everything installed, and then the BBU comes afterwards. So nowadays, the installation crews need to have both RF and fiber experience. So getting to know a lot of different test gear that wasn't traditional from before, and we're going to talk a little bit about that also. And lastly, when we talk about the reason for a BBU test, which we'll get into, is the ability to speed up the test, and we'll talk a little bit about the benefits of this. First, we'll just a quick review of CPRI. And CPRI, normally we talk about two layers, the physical transport, which is your fiber, and that could be in either single mode or multi-mode. Single mode is more traditional now. Multi-mode was installed more earlier because of cost differences. Single mode is used for long runs, and multi-mode is usually used for the short runs that are going up straight up a tower. In layer 2, we are looking at the IQ data. The IQ data is what gives us the ability to do RF measurements from that fiber optic link. And now with BBU installation, you start looking at the control and management plane, or CNM, and that's where we basically send and receive the BBU commands and the response from the REO. CPRI's got a lot of line rates. With the new release 7, we have now gone up to line rate 10. That gets you to 24.33 gigabits per second. In most cases, I've been running into line rates 3, 5, and 7. Those are the most common ones out in the marketplace today. So you're going from 2.4 to about 9.83 gigabits per second. The line rates basically are what's your throughput. It's also the amount of information that's given within the CPRI frame that can be transmitted. Now, some key differences between a traditional RF and CPRI. RF, once it's being transmitted from the antenna, is basically an analog system. CPRI is all digital. In the RF world, you're looking at absolute measurements in dBm, and then CPRI, it's usually relative measurements in dB. In RF, again, you tune to a specific center frequency for your signal that you're trying to make a test on. And CPRI, everything's baseband, so it's basically frequency agnostic. So any radios or multiple radios or multi-band radios can be sent down the CPRI, the fiber optic link with the CPRI protocol, and it's going to come down at 0 hertz. The other thing with big difference is we are looking at any spectrum-based measurements. In RF, you can go full span or narrow as much as you want. With CPRI, there's only so much IQ data that's sent down that fiber link, and that's what's going to limit the maximum span you can have on your fiber optic cable. I'm sorry, that's going to limit the span that you're going to see on the spectrum analyzer. Some key parameters are line rate, again, the throughput, the AXC or antenna container group, CPRI bandwidth, which is basically the bandwidth of your LTE carrier or any other technology, IQ bit width, so that's the length of the word length of the frame for the CPRI link, and reserve and stuffing bits, which are fillers. So let's say if you have a IQ bit width of 15, then you normally have a reserve or stuffing bits of 0, because you'd have 15 I bits and 15 Q bits, total of 30 bits, which fills up the frame. If you go on the uplink, a lot of the configurations use 12 IQ bit width, so then you would use 3 reserve or stuffing bits to get you that 12 plus 3 equals 15 I, and 12 plus 3 equals Q, and total of 30 bits. And the CPRI aggregation is for some, I'll call it legacy systems that were, when LTE first got deployed, some systems only use 5 meg carrier, and they stitch together 5 meg carriers to make, let's say stitch 2 of them together to make a 10 meg, or 4 of them together to make a 20 meg carrier. And then that's also sent down the CPRI link as individual 5 meg carriers that you have to be able to understand that needs to be stitched together to create a wider signal. Okay, so what is the value of BBU emulation? Main reasons for BBU emulation is faster turn-up time. So carriers can collect revenue earlier from a new site that's deployed. Contractors can be a little bit more profitable because they don't have to keep returning to a site. And that comes down to what's traditionally happening today, which just talking to a lot of folks out in the marketplace, there are normally 3 to 6 truck rolls necessary to fully commission a site right now, because installers come in, do their work with the fiber, the remote radio head, the antenna, the jumpers, they leave, somebody else comes in later, has the BBU, turns it on, tries to commission the site, and something's not correct, so it won't work. And it normally takes multiple visits to get everything worked out. So by being able to do BBU emulation, you can lower your OpEx cost. In particular, it's really applicable mainly to new construction. It allows you to test the remote radiohead infrastructure without a commissioned BBU, so validates that the installation work was correct, that everything that you installed is working properly. We'll get into a little more details of what kind of tests are there and what things you're looking at. And the other big thing is, if you do find faults, is that you're already there with the construction equipment, the lifts and so forth in place. So you don't have to rent them again. You can actually just use those to fix any problems that are found with while using a BBU emulation test. For existing construction, so if it's already a system that's deployed, this allows you to validate whether you need to replace a BBU or a remote radiohead by either by testing a site that's not working properly. So you can first monitor it with a tap and see if you're actually seeing something coming out of the BBU, or you put this in place, talk to our remote radiohead and see if you can get it up and running. This allows you to figure out, do I need to change the BBU or do I need to actually call a tower crew and change the remote radiohead? And the reason I mention this is that from a lot of customer visits, in some cases they're just swapping out initially BBUs, and then if that doesn't fix a problem, then they go up and swap to the remote radiohead. So that will get you some, if you're replacing a component and then you're sending it back to the equipment manufacturer, you probably will get some what they call no trouble found, or NTF cost charged back if the unit was working properly. So it allows you to not have to replace good equipment and reduce overall cost. So normal installation tests include, you need to do, you still need to do sweep your cables, your jumper cables and the antennas. One of the things you have to do with any type of fiber installation, it's very similar to, we'll say, PIM. You got to be really careful and keep all your connections and the fibers clean. Make sure the ends are clean, make sure the SFP connectors are clean. I've been told some stories about where they kept plugging in their fiber optic cable, and when they unplugged it, they noticed the fiber was dirty again because something had gotten into the connector itself. So make sure you practice get cleaning with all of your fiber components. With being able to test the remote radiohead with the BBUs, you figure out if the SFP is installed in the correct place and if it's also the correct SFP to support the line rates that you want. And you can also do a full functional test on the remote radiohead, make sure that it's actually transmitting over the air and working properly. So normally, to do all this, requires your VNA for line sweep, for the jumper cable antennas, a visual inspection probe. In some cases, some folks like to use OTDRs, and you need your SIPRI BBU emulation tester. Another thing is there's different configurations. Let me go back here. In this configuration, you're running a individual fiber from the BBU back to the remote radiohead. Another configuration is that you can run from the BBU up to one remote radiohead and then daisy chain other remote radioheads to it. So this simplifies running a fiber up a tower or from a long distance location. The one downside is if that fiber gets cut, you're taking the whole site down as opposed to taking a sector down. But in this case, what happens is you have the master clock from your test equipment that's running up to the remote radiohead to the fiber, and that's usually placed into port 1 or the slave port. The master clock slave terminology comes from IT, but you just want to mention that so it's always going to be a master slave, and then on the RH there's another master port that then goes to the second RH port 1 or slave port, and so forth. So that's how you end up daisy chaining the different radioheads together. Now the problem is if you install the SFP in the remote radiohead in the port 2 or the master port, what happens is both the remote radiohead and either BBU or the tester thinks they should be the master clock. So there'll be some conflict going on, so you'll never get a SIPRI link up and running. So the idea is basically to have one master clock that is coordinating the whole system. So to set up a BBU test, you end up, first you make sure you have power to the remote radio head. It's real basic, but you want to make sure that that is up and running. Make sure the SFP you're installing supports the required line rates. Usually that should be something that's given with the kits that are given to the installers to place up on the tower. Make sure everything's clean as far as the fibers and the connectors. Connect all of your, well, this is also assuming you've already installed the antenna, installed the jumper cables. You'll connect a duplex, so that's a transmit-receive fiber pair to the SFP and the RH, connect that down to your test equipment. And it's pretty simply, you put your test equipment into BBU emulation mode. At that point, the test equipment goes into master clock, and the units, and I think it's in this next one, when you start the BBU emulation mode, the SFPs auto-negotiate the line rates that they should be going at. So you'll see some delay, and actually I should step back a little bit. When you're doing BBU tests, they're expect to have anywhere from 20 to 30 or 40-second delay with some of these commands. It's not like a normal RF test that you're doing on test equipment when things kind of work instantaneously. So it's basically a send-receive kind of sequence. So you're sending commands, waiting for the acknowledgments and response. So you have to have a little bit of patience when you're doing these types of tests. So the first thing that's mentioned, the equipment auto-negotiates between the tester and the SFP and the remote radio head. And in this example, all of the lights turn green. Once that is accomplished, that means you have a valid SIPRI link between the test unit and the remote radio head. Then you basically want to initialize or request information from the remote radio head. So before this happens, all you've done is set up a link between the two SFPs. When you've requested initialization, you're looking for, now you're talking to the remote radio head. In the example we're showing, we're using the Ethernet link within the SIPRI protocol to contact and send commands up to the remote radio head. And after some time, you get a response back, which has the IP address of that remote radio head. If you have multiple remote radio heads, you'll have multiple IP addresses, and they will be in the order that they are deployed. The other thing is when there are a couple different ways to send CNM commands to the remote radio head. So the example I'm showing is Ethernet. The other one is HDLC, which is high-level data link control. And there are some equipment manufacturers that use a proprietary method. So in this, as I mentioned before, if you do have multiple remote radio heads, you do get the active links. Again, you just have to have a little bit of patience. I know it's in this world, if you are an installer, you like to do things really fast, but at the end of the day, this doesn't take too long. Will give you lots of benefits as far as getting your work done properly. So repeat again, in a daisy chain configuration, each radio will request the IP, will send back its IP per the request, and they'll come back in the order requested. Now what you have to do is click on the IP address that you're interested in, which relates to the radio that you want to test. And it sends a set of commands saying, hey, identify yourself, who's the manufacturer, what's the model number, what firmware do you have running, what frequency range do you transmit at, what's the power levels that you transmit at, and so forth, where's the SFP that's installed located, in which port. So all that information comes back and is displayed on your test equipment. That helps you validate, hey, is this the right model number that I should have installed at that site, at that sector, in that location? look at the frequency range, the power range, and also is the SFP located in the correct port, which I've been told is one of the most common errors, which we'll show you a little photo to see why, because it's pretty, they're not exactly marked very well. So again, reading the other thing you can do is actually do a SFP test. So you can actually query the SFP once you're talking to the remote radio head, and then the SFP will report back its information. So the wavelength, you know, if it's 850 nanometers, it's a multi-mode. If it's 1310 nanometers, it's a single mode SFP. The bit rates supported and so forth. And then below that, you can get the vendor name, in some cases the serial number, the build number, and so forth. So you can actually keep track of what's working. And here's a picture of a remote radio head. You know, the markings don't always say, you know, in this case it says CIPRI 1 and 2. So you have to, and it's painted in the same color as the casing. So you have to be able to see that and make sure that you're putting in the SFP in the correct port. So one of the things to do a lot of the functionality tests on a remote radio head, you need to load a waveform file and load it into the remote radio head and have it transmitted. So these are typical 3GBP waveforms that most BBU solutions have. They come in different wavelengths, or bandwidths, I should say, 5, 10, 15, and 20 megahertz, and then the given models are there. So I'm actually going to cover them a little bit, and I'll make you 2 recommendations on which ones are probably the most likely you'd want to use. So test model 1.1, and by the way, the description of what it does down below came from the 3GPP spec, which I'm showing down below, the TS36.141, section 1.1. And if you go there, they're going to give you in fine detail for every bandwidth how many elements are being used, what power levels, and so forth. So it gets pretty complicated. But these are typically done to test occupied bandwidth, adjacent channel leakage ratio, unwanted emissions. So it's more of an RF-based test. So you'd probably be wanting to, if you're going to do this, which you'd use this with a RF-based tester up at the tower. Similar for the 1.2, again, it's for unwanted emissions and ACLR. Test model 2 is one of the ones that I do recommend because it's really transmitting, it's using 64 QAM, it's also using min power. So if you want to have a baseline of your noise floor on the receive path, you can use this in case you want to test for PIM. And then the next one after this is actually transmitting at max power at 64 QAM. So all the PRBs are transmitting at max power, which is test model 3.1. So test model 2 can give you a good reference for your noise floor. Test model 3.1 will transmit max, and if in reality, if you have no PIM, that noise floor shouldn't change. If you have PIM, you'll see something rise, and this is a quick way to test it by using these 2 test models. And test model 3.2, it's using 16 QAM modulation. It's usually used for frequency error tests. And then test model 3.3 is using QPSK. So it's each test model in the 3 range is basically sending out the 3 typical modulations that are used in the LTE world today. So that's where we get into transmitting from the RH. So like I mentioned before, you're going to load a LTE wave file up to the remote radio head. You'll have to wait a little bit because these can be quite big. The RH will say, hey, trying to load. Once it's finished loading, you'll send back an acknowledgement that the wave file has been loaded into the unit. You can, well, and before you do anything there, you also can pick your, you usually want to pick your center frequency that you want to transmit at. Remember that with the BBU software that's running on your test equipment, you've already when you initialize the remote radio head, you downloaded what frequency range it works at. So you really can't choose any frequency outside of that. And in fact, most the test gear will not allow you to. to put anything beyond what's actually available for that remote radio head. The same thing is for the output power. So you've downloaded what's the max output power you can transmit, and that will also be limited on the test equipment software. So you pick your frequency, you pick the transmit power, output power you want to have. You've already picked the waveform, so either test model 2 if you want to get baseline on your noise floor, test model 3.1 if you want to simulate OCNS, which is what transmit full power on all the RVs. And then start making some, basically turn that on, and you can start making a few different measurements. So one of the things you can do is have somebody with a spectrum analyzer making over-the-air measurements, validate that the sector is transmitting its LTE signal. If you want, you can also go into demod and demodulate that signal to see what's happening. I believe that's not really part of the MOPS right now, the procedures, but it could be in the future if that's if there's enough value there. But it's definitely useful for troubleshooting existing installations. Next, you can also do a return loss or Viswar measurement with when the radio is transmitting. Basically, you're using the radio to make that measurement. So similar to what you'd get when you have a unit already installed and you're making a request from the switch. So you're basically telling the remote radio head to do a frequency-based measurement for return loss and Viswar, and you can see those results on there. You can set pass-fail limits and figure out if if those values are within range, or if you need to go back in and make some adjustments or clean up ports or tighten ports. More than likely, so tightening your connectors. And you could also, this is what we're talking about, using test model 2 and then using test model 3. So if you want to look at for any possible PIM in a system once it's installed, you can use 2 to baseline it, use 3.1 to transmit max power, see what happens on your uplink. Also, you'd want to use your min-hold trace as well as what's your normal trace to validate that it is PIM, because if the min trace stays very low, flat, then you probably don't have PIM, but it could be a separate interference issue. So after the BBU's been fully installed and commissioned, you can still go back and test the system. So you go back here, go back one slide. So at this point, you've done your RF functionality test, you've done your SFP functionality test, you've done your CPRI link functionality test, and now you've looked also for interference or PIM issues on new construction. If this is all working properly, when a BBU is brought in after the crews left the site, it should go up and work properly that first time, and should not require that a crew come back and troubleshoot it. Now, if you are troubleshooting fully commissioned sites, you typically, in this case, will use an optical tap. In some cases, some carriers are already installing these in their sites. In other cases, you bring your own tap, put it between your the BBU and the remote radio head. And at this point, what you're doing is basically tapping in and monitoring the existing live network. You have to make sure that you are in normal CPRI mode as opposed to BBU mode. So you're not in master clock, but now you're just listening in the slave mode. In this case, you can make all of those same measurements. Actually, you can make the uplink RF measurement, check for any interference or possible PIM issues. And also, you can even check the downlink, just validate that the BBU is transmitting its LTE signal. And that's what we're covering here. Is just, again, validate no interference, because that will impact your KPIs. So to summarize for BBU emulation, so in a sense, what your BBU emulation basically is what it sounds like. You're emulating the BBU. So it allows you to verify the remote radio head system, the components that are installed, that components are installed correctly, and also verifies the complete system functionality. So like I mentioned before, your SFPs are installed correctly, you can get a CPRI link up and running. You can transmit an RF signal. You can look at the uplink, validate that that's clean. That also checks that the antenna and jumper were installed properly with return loss and Viswar measurements, as well as the looking at the uplink to see if there's any possible PIM issues. Also, it allows the installers to basically find and fix any issues on site. So that first time when you get everything running, if anything's not working properly, you can still get up to that tower relatively easy with all the equipment there. And that should reduce overall site turnup cost, should reduce the cost to installers in the sense that you don't have to go back. Because I know many times now there's fixed pricing, so you get that site up and running, and if you have to go back multiple times, it's on your dime. So this allows you to do this a little quicker. The operators benefit in the fact that this also gets you up and running faster, so you get revenue from new sites much faster. And it's useful for troubleshooting existing installations. Instead of swapping out BBUs and then RRUs, you can put this in line if you need to, and you just validate that one or the other is working properly before making that decision. And again, lower your no trouble found cost. So that's it for BBU Emulation. Thank you very much for attending, and I guess we'll cover the Q&A session.
Yeah, thanks, Emilio, for that very great and in-depth presentation. So we've had a few questions come in. The first one is, how fast is the BBU test?
So as I mentioned before, it's going to vary. It's actually going to vary between RRH models, and it's going to vary by the functionality. So each individual test can require 30 to 40 seconds for a full response, and then actually and measurement. Once the transmitter is actually working, where you have the waveform file loaded and transmitting, all the other RF tests are actually relatively quick.
Okay, next question we had come in is there any signal routing or switching function in CPRI link between BBUs and RRHs as opposite to one-to-one mapping?
As far as the only, I wouldn't say there's any like switching. I think it's basically daisy chained, and in the case we're looking at, it's IP address based. So the only way you switch to a different RRH to test is by switching the IP address that you're choosing, that you're going to place under, that you want to send commands to and test.
Okay. Next question: which test modes are recommended for PIM testing?
So I would say test model 2 again, because that is min power. So that kind of helps you baseline your noise floor. And test model 3.1, which is basically max power on all the RVs. And that's going to stimulate any possible PIM issues you may have in the network.
Okay, and a couple of questions about equipment manufacturer. So the first, which equipment manufacturer does the BBU solution support?
In our case, it's the ex-Alcatel-Lucent or now Nokia equipment.
Okay, that actually answered both of them. I believe there's different requirements for each of those. Is that correct?
Yeah. So what we've created different scripts for different models. So each one is slightly different in what they're expecting from a request response kind of way. And then from different vendors, yes, there's different, the same thing, there's different operations and different actually ways that you talk to the remote radio head. That's I think it's the HDLC. That's for one manufacturer, that's what they prefer. And well, actually one or many manufacturers. So there's, again, multiple ways that you can talk to a remote radio head.
Okay, gotcha. And I think this is kind of a related question, but does the BTS master care if the RRU is under test as insert vendor here? So does the BTS master care if the RRU is a specific vendor or not?
So for BBU tests, yes, because we do have the commands set for, again, like the Alcatel-Lucent Nokia equipment. For CPRI RF measurements where he's putting the tap in line, we can talk to more vendors. So in our case, Huawei, Ericsson, and again, the Alcatel-Lucent Nokia.
Okay. Next question. So can a user transmit on any frequency?
Only the frequency that's the remote radio head response backs on. So if it says it can transmit for generic say 700 to 800 megahertz, then that's the range that you would be able to transmit in.
Okay, and then oops, sorry. We just got this other one. Can you describe the PIM detection and VSWR measurement process again?
So the PIM detection is basically it's an RF basis measurement. So it also requires somebody who's probably done it a few times to realize what's going on. So you run test model 2. It helps you baseline the noise floor, and you do that with a min hold on your trace. So that way you get your min hold with trace model 2 or test model 2 running. Then you switch to test model 3.1, which is max power on all the RBs or resource blocks. And then in reality, if there's no PIM, that noise floor shouldn't change. If that noise floor all of a sudden rises, then there's a strong possibility you do have PIM, and then you would bring your PIM tester up to the top of that remote radio head at the top of the tower and make your RF-based measurements then. And the other one is the Viswar. So what we're doing is we're actually using the remote radio head. So it's remote radio head. The remote radio heads are not like a normal VNA, so they're not made to sweep. So we're making this a frequency-specific Viswar or return loss measurement. That's testing the jumper and the antenna.
Okay, next question coming in, somewhat of a follow-up. Can you do PIM analysis also with the BBU emulator?
Again, was that okay? Again, it's a RF based, and it's also just looking at your noise floor. So it's, in a sense, it's a noise floor based measurement at this time. Again, you're just looking to see if when you're transmitting at max power, is that noise floor rising? So it's basically a correlation between the downlink and the uplink. If you have PIM, when you transmit, have a strong signal transmitting out of your radio, and you have a third or fifth order intermod, and it happens to fall into your receive band, that will show up as a rise in your noise floor. And because LTE is a wideband signal, it should be a wideband noise. If there is no PIM and you transmit at full power, your noise floor is going to stay stable. It's not going to rise. So it's basically, at this point, a noise floor measurement.
Okay, perfect. Next question we had come in, can the unit verify a link with RET cables connected to the AIG ports?
To R8? Hold on a second.
Sorry, RET cables connected to the AIG ports.
Hey, Mike, you want to help me on?
So talking about like remote antenna tilts and those kinds
of
things.
Gotcha. So at this point, we don't have that working. So it's the RET and the using the ISG. So that is something we do have planned for near future. What happens, it's the same process. You're sending a command receive to the remote radio head. Remote radio head has a cable that sends that AISG command to the RETs, so the antenna tilt system, and then validates that that's working properly by basically tilting the antenna and seeing the response back. Or if something's working improperly, you'll get an alarm. So so it's either a good pass or a fail if you get alarms back from the RET modules themselves.
Okay, perfect, thanks. So in one using daisy chain mode, how do they know which RRH they're communicating with?
So when in this case with the again the Nokia Alcatel-Lucent gear using the Ethernet, so we actually will talk to the first radio first, because that's setting up that first communications between the master clock and the port 1 up top. And then we'll get a response. Once that response, it'll actually then going out through the other port 2, which is they're passing on the master clock to the second remote radio head. Then they'll get a response back from that one and give us an IP address that will be listed second, and the same thing with the third one. So basically the order that they're displayed gives you the order that they're installed or you're talking to them. So the first IP address will be the first radio that's connected to the long fiber. The second one will be the second radio is connected to the first radio, and the third one will be the third one connected to the second radio.
We had a bit of a follow-up question. So is there any difference to test remote radio heads in daisy chain or single fiber?
I guess the only difference really is that you're looking at multiple IP addresses and you're switching between them. Again, the biggest issue or difference really is that from an operator standpoint is, do you want to just rely on one point of fault? If something happens to that main fiber, your whole site's down. Or do you want to go with single fiber to a radio? Though and I know that doesn't work for every application, but a single fiber to a radio basically at least says that if you lose one fiber, the other two sectors are still working.
Great. So next one, can you control or adjust the antenna tilt with BBU emulation function, or is there another type of controller that's needed?
Well, for us, not today. Like I said, it's something we are going to be adding. So you can add, but you can't do that through BBU emulation.
And then also, can you talk a little bit about reporting? So does the instrument actually record results and provide some sort of report?
So for us, we work with our, we have different software tools that are available through Rrihs that come complementary with the equipment. So we can actually take in those measurements or screenshots and make reports from that information using the software. So not straight from the box, but with the software that comes with the unit, yes.
Okay. Just looking at a couple more here. As for DTP, distance to PIM, and PIM analysis, is that something that is done with a BBU or can be done with a BBU, or is that technology and process all completely different?
Well, I mean, like I said, if we do the for right now, if we use that, we make the noise floor measurement, we can determine if something's there. Then you would actually connect your, say, PIM master, for example, that does have the distance to PIM capabilities, and that's an RF-based test. Right now, through BBU emulation, we're not currently doing that. Obviously, I think that's the #1 question everybody's giving us. So it's something we are working on, but at this point, I'm not going to say when or where.
Yeah, definitely. All right, that looks to be most of the questions here. So another one we have is, can one test the receiver without having the transmitter on?
No, you actually need to have the transmitter transmitting out a signal to turn on their receiver.
Okay, just looking at the questions here. We have had a couple more come in.
Mm-hmm. So I know this one's come up. I'll answer this. It's some of the vendors, in this case I've mentioned Huawei, they test PIM and Viswar. So like I said, we are doing basically the same Viswar tests the vendors are doing. The thing is, we're doing it without the BBU commissioned. So it's when the BBU is not commissioned, it's basically there's no data going back to the NOC. So it allows the install crew to basically validate that. The same thing for a PIM test. I know some of the vendors do some basic what they call PIM. Though the funny thing is, I just been out traveling around the world literally about a week ago, and carriers that use a lot of these vendors were asked, #1 question was PIM over CPRI. So I think some of the vendors have some type of solutions, but it doesn't seem like a lot of the carriers are as happy with those solutions. And I guess I'll leave it at that for now.
Okay, perfect. So we had another one come in, is when performing a BBU emulation test, do you need a separate RF spectrum analyzer to test over the air, or can you just use the same Rrihs tester used for BBU emulation? No,
you do need to have a separate tester, because you actually still have that communication link with the through the fiber. So you can't basically, I guess you shouldn't really disconnect from the remote radio head if you're trying to do an over-the-air test. So you would need a second unit.
Okay, looks like we had a couple questions asked about the license needed to use a BBU emulator. Do you have any insight as far as kind of the licensing process for use?
Yeah, it's just an option. If you already, for example, if you already own one of our CIPRI RF CIPRI card in the BTS master, you can actually just buy an option for that existing card.
Perfect. Looks like we have time for just one more question, and we've had a lot of questions about OEMs and users. So just to wrap up, can you just kind of highlight again which OEMs are supported on the BBU emulation at the moment?
So at the moment, it's the old Alcatel-Lucent, now Nokia equipment.
Mm-hmm. Perfect. All right, that was a great presentation. I want to thank everyone for joining today's presentation titled BBU Emulation, Saving Time, Saving Money, and Saving Headaches, presented by Rrihs. Again, our presenter today was Emilio Franchi, Senior Product Manager at Rrihs. Emilio, thank you for leading the discussion today on BBU Emulation. I think everyone learned quite a bit, so thank you so much.
All right, thank you, Kyle, and thank you everyone for attending.